Hello, in this lesson we're going to be learning about the moment of inertia. So the moment of inertia is denoted by the letter or symbol capital I. Okay, and now we're going to start the explanation by going over the equation for the moment of inertia. So the equation for the moment of inertia is equal to the sum on I of all of the masses multiplied by their distances from the axes of rotation squared. Okay, so what does that mean? Let's say that we have over here our axes of rotation. It's going upwards in the positive z direction, and then we have some kind of rod, okay, like so, and it's rotating in this direction about the axes of rotation. So what we're going to do is we're going to split up our rod into tiny little segments, okay, where each segment is of mass mi, and we're going to measure the distance also of each segment from the axes of rotation. Okay, so this distance over here is going to be ri. So then we take our ri squared and multiply it by mi, and then do the same thing for every single bit along this rod, and that is how we find out the moment of inertia. Okay, so that's a little bit of a mathematical explanation. Intuitively, we'll understand it and explain it a little bit more later. I don't want to go into it now, but a way of thinking of the moment of inertia is thinking of it as mass. Okay, now I'll explain it a little bit later why it's a good idea and why it makes it a lot easier to consider the moment of inertia as similar to a mass, and let's carry on with the explanation. So now what we're going to do is we're going to do a worked example of a much easier example. Okay, so here again we have our axes of rotation. Okay, and here we have a point mass of mass m, and it's located a distance r away from the axes of rotation. Okay, and this point mass is rotating around the axes of rotation. So let's work out the moment of inertia. So I is simply going to be equal to, so we only have one point mass, so it's going to be the mass of the point mass, so that's m, multiplied by its radius squared. So its radius is its distance from the axes of rotation squared, so that's r squared. Okay, so this I advise you writing in your equation pages. So this is the moment of inertia of a point mass, and we're going to be using this in examples, so it's useful to remember this. Okay, so now what happens if I add in another point mass of equal mass m and the same distance over here, r, away from the axes of rotation? So now what will my moment of inertia be for this system of 2-point masses rotating around? So as we can see from the equation, it's the sum of mr squared. So we're just going to have mr squared plus mr squared from this side. Okay, so that's simply going to be 2mr squared. So this is the moment of inertia of 2-point masses rotating around an axis of rotation. And also don't forget to copy out this equation, over here. This is very important. Okay, so now let's take another example. So here we have the axes of rotation, and about the axes of rotation we have a disk, okay, and the disk is of radius r and of total mass m. So now what we want to do is we want to find the moment of inertia of this disk which is rotating around here. So what we're going to do is we're going to take small portions of this disk, okay, of mass each one dm, and then we're going to sum up on all these portions and plug it into this equation. Okay, so let's see how we do that. Alright, so when we deal with a shape like this, where we have lots of masses dm. So the way that we're going to use this equation is we're going to use the exact same equation, but with an integral, okay? And we're going to integrate along the entire disk.